screen. Okay, so hi everyone, good afternoon. Thank you for joining today's webinar series. And then for today, the topic is a basic explicit dynamic. The main objective of today's webinar is to provide the audience, the participant, with the basic of explicit dynamic, so that you're able to perform some simple explicit dynamic simulation. Okay, so for today, we will review about the word solver used to solve the explicit problem, application of ANSYS Explicit Dynamic, and then basic function in ANSYS Explicit Dynamic. And then we perform basic explicit dynamic, which is the Taylor test. And if we have more time, we will I will show you step-by-step procedure performing a drop test using a drop wizard, drop test wizard. Okay, so when we talk about the explicit dynamic problem, actually ANSYS offer you three solver, which is LS, Dyna, Autodyne, and an explicit dynamic. So for LS Dyna, Autodyne, and ANSYS Explicit are all EFA software used for the simulating dynamic event and behavior. However, they have differences between LS Dyna, Autodyne, and Explicit Dynamic. Basically, LS Dyna and Autodyne are more specialized, used in a more specialized area. Focus, for example, LS Dyna in the nonlinear dynamic and Autodyne in the shockwave simulation. Okay. However, for the ANSYS Explicit Dynamic offer broader scope with integration possibility within the ANSYS ecosystem. So what I can say here, ANSYS Explicit Dynamic is more general compared to LS Dyna and Autodyne. Okay. This is the application of ANSYS Explicit Dynamic. Okay. So some common application of ANSYS Explicit Dynamic include crashworthiness, drop testing, high-speed impact testing, and so on lah. Okay, this is an example lah for the hypervelocity impact. Okay, this is a simulation, one of the simulation example here. And then for the penetration, okay, so this is a example of simulation for the penetration. Okay, so basically you can use ANSYS Explicit Dynamic in many applications. So it depends on the problem that you want to solve it. Okay, so before I begin more detail about the simulation, so you need to determine the difference between implicit or explicit method. Okay, so implicit and explicit method differ in their treatment of time integration. Okay, so basically we use the implicit method for the static problem or less function problem. That means more than 1 second. for the implicit method, actually we use for fast and extremely non-linear dynamic problem, which means less than 1 second. Okay, and then explicit method solve this is the how the solver operation lah. Okay, and then implicit method used for have a high stability compared to the explicit method. Okay, so from this image, you can see more detail. Okay, so this, for example, the implicit method is a creep, static dynamic, and quasi-static. So you select this implicit method when the time is more than 1 second and is involved less nonlinearity. So basically, anything then less than 1 second is the explicit problem. So for explicit problem, normally you can use for problem or simulation that have a high nonlinearity. For example, drop impact, ballistic, detonation and blast, and also hypervelocity impact. Okay, smaller time step might be required to accurately capture intricate nonlinear response, especially when dealing with the highly nonlinear material, complex geometry, or contract interaction. This is for the implicit method lah. Okay, so now I will begin with the basic explicit dynamic. Okay, so you can, in the workbench, actually you can select the implicit dynamic here. Okay, and then you can drag to the workbench. So as the performing the static structural, okay, the flow is the same. So first you start with selecting generating data, and then go to load the geometry, and then model, setup, solution, and so on. So this is the step lah, the basic step for the explicit dynamic simulation. Okay, and then so for the when you select the engineering data, you can select the material here. So it depends whether you can create a new material or selecting existing material from the library. If you select a material from the library, actually you can, in the explicit dynamic problem, you can choose two type of material from this library. You can select from general nonlinear material, or you can select a material from the explicit dynamic. Okay, so you can see below here is the material for the explicit material. So there are many material that you can use. Okay, next is about the body interaction. So body interaction you can find in the connection tree. Okay, so in the explicit dynamic problem, this is very important. You need to define body interaction properly. So what is the body interaction? Actually is used to define a global connection option for explicit dynamic, and used to give a surface to surface contact between different material. So this is the purpose of body interaction. Okay, if you open the body interaction, you can see this feature. So in the body interaction, you have a contact detection, and then formulation, sliding contact, body cell contact, and element cell contact. By default, the contact detection is set as a trajectory. So trajectory contact area is the default, and recommended option is most case for the contact in explicit dynamic analysis. So so what is the difference between body interaction and contact? So this is as I mentioned before lah. Body interaction specified contact between body, but contact is a specified contact between surface. So body interaction more simple compared to the contact. Okay. Next is about the meshing. So in meshing, for the explicit dynamic problem, explicit is set as the default for the physics preference. So so make sure that you use this physics preference for meshing, and then for global meshing, the setup is same as the static structural. And then you also can localize meshing by insert use a different type of method. So there are many type method that are available, but for the the preferred method for the explicit dynamic is the Swag and Martinson. Okay. After you perform mesh, you need to check the quality of the mesh. So you can use two feature here, which is a mesh display style or mesh metric. Okay. In both of these feature, always select characteristic length. Okay, because characteristic length is an important information that define the scale of physical system. Okay, actually characteristic length actually determine our critical time stack. So later I will explain more lah about this critical time stack. Okay, so the effect of time stack. Okay, so in the analysis setup, so you need to careful select the time stack. Okay, because the higher or larger number of time stack mean more computation time are required. So okay, so you need to define carefully the time stack. So it's advised to start with the smaller time stack. Okay, because this is you can check after you solve the problem. Okay, you can always check the time required. So if you start with the higher time stack, mean the longer time required to solve the problem. Okay, and then in the solution information, also you can check the energy. So this is example lah. Later we do the simulation. You can see more detail about the energy, time step, and so on. So now I will begin with the simple simple problem, which is the Taylor test. Okay, so sorry, this is the Taylor test. Okay, so the goal, okay, we will do this simulation. Okay, so before we start with the simulation, we go to the engineering data. So as by default, the basic material that set is a structural steel. Okay, so now you can go click to the engineering data source to insert a material. Okay, for this case, I will use the two type of material, which is the aluminum alloy, and then okay, another one is the style structural steel nonlinear. Okay, so as I mentioned before, actually for explicit problem, you can use whether you can define your own material or you can select from the library. Okay, for this case, I use a nonlinear material. Okay, after you select, you can go back to the workbench, and then now we can start with the modeling. Okay, so right click and then click yes here. Okay, so this is our model. Okay, so for the material cylinder, we set to aluminium alloy nonlinear, and then for the plate, here I will change structural steel to the structural steel nonlinear. Okay, so make sure the unit is in meter, kg. This select this unit. Okay, so next we go to the connection. So this is a body interaction, just as I mentioned previously. But for this case, you can delete the contact because in the ANSYS in this simulation we don't need to define the contact, so you can delete, and then okay, and then this I think you don't need to change. Later we will check here, but for now we go to this body interaction here with S. So make sure you select the frictionless because the cylinder and this plate are not bonded together, so it's only touch. Okay, so basically by default the type the type frictionless is set as a default lah. Okay, so now anything is correct. Then we go to mesh. So make sure that the physics preference is explicit. So for this case, I will change the element size to 0.03. Then for sizing, this use additive size change to no. Okay, so actually the other setup I not change. I set as a default only. So and then you can generate the mesh. So this is the mesh. So okay, you can check the quality of mesh by this one characteristic length. So this is the the quality of the mesh, but also you can check the quality of mesh by refer to, then go to a mesh metric and then click characteristic length. So here the okay. Okay, next you can define the boundary condition. So can insert the velocity or angular velocity drop height, but for this case I just define the velocity. Okay, so I will select this body, and then you can always change this defined by component. So you can refer. So refer to the ANSYS because now I want to define this velocity on the negative direction of the axis. So for this case, I define 300 meter per second. So the direction to the wall here. Okay, now go to the analysis setting to define the end time. So for this case, I use this. Okay, always start with the smaller end time. Okay, basically you can also define the initial time step, minimum time step, and maximum time step. If you unsure about the exact time step, so you just let the program let the program decide. Okay, so okay, that's all. Okay, so and then I will insert one more boundary condition, and I set this surface for the fixed support. Okay, and then you can define insert the directional plot request, and then select the Z direction. Okay, and then for stress, okay, and just select equivalent plastic string. Okay, now I think you can solve the problem now by click the solve. Okay, during the you can go to the solution information to check. So this is a time required to solve the problem, which is about less than 20 seconds. So the more complex problem require more time. Okay, now the problem solved already. Okay, actually you can also go to here, energy conservation, to check the energy. So this is the 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 solution. Okay, you can click the directional information and then click play to see the effect of the simulation. Okay, actually we are done with the first simulation. Next, I want to continue with the another simulation. Okay, the second simulation is the drop test. So firstly, we need to define the material that we want to use. So first, we click to the engineering data and then right click, then click edit. So this is the material that we will use, which is aluminium 6061, and another one is a PCB. So all the material property already defined properly based on the material. So now we go back to the model. Okay, right click and then click edit. Now we want to open the model. So this simulation um, the goal is to use the drop test result to simplify the setup of drop test simulation. Okay. Okay. So first, we need to make sure the unit we use is in meter, kg, this one unit system. Okay, and then we need to define the material. Then for the CPU and memory, CPU and memory we define as the material we assign is PCB, and then for the PCB part is PCB part as a PCB. Okay, and then for the thickness is 0.0002 meter. So make sure the unit is correct. Okay, and then we already defined and then for the heatsink, and then the material is aluminium 6061. So and then we go to the mass sizing. So the basic preference which is explicit, it is set as default, and then the element size is 0.0003. Then for the capture curvature, we return we switch to yes. Then for the curvature minimum size, we change this one to 0.03. Okay, and then after that we can right click and then generate a mesh. So this is the mesh. Now we go to explicit, then go to the environment, and then click here to activate the drop test wizard. So this is a drop test wizard. So it will take time to load the. Okay, so this is now the drop test wizard. So for the target rotation, we remain as a default, which is 0. And then drop rotation, we change this one to negative 25. And then for drop rotation Y and Z, we don't change anything. Okay, but for drop height, okay, the impact defined by the drop height, and then drop height is 1 meter, and then after that we can select next. Okay, and then for the frictional behavior, we keep as a frictionless behavior. Then okay, and then after that we can click finish. Okay, after okay, we need to okay now we need to review. So there are the drop chain, the test wizard chain several part here. So which is part transform, and then it will create a then it will create a fixed support, and then standard 8 gravity, and then add the deformation, plastic strain, total acceleration. Okay. Okay, and then now we go to the body interaction. Here is body interaction. Okay, set, and then we can set the sheltered factor is 1. Then self body contact we can change to yes. And then this one also we can change to yes. Okay, and then after that we can go to solution information, and then we can insert contact force result. Here, then this one, we can select this, and then this one we can change the orientation to y-axis. Then for the total duration, can select this part. And then for this part, we can okay. We can hide the heatsink part, and now we can solve the problem. Okay, we can monitor the solution here. So the solution will take approximately about 7 minutes, and it will be terminate normally. So here, the solution took about 15 minutes to solve the problem. So we need to wait the before we obtain the solution. So now the simulation is complete. So we can see we can run the simulation. So, this is the result for the total deformation. You can see here. Then it is the result for the equivalent plastic strain. And then the last one is the total result for the total acceleration. So that's all for today. Thank you for your time. And then we can move to for the Q&A session. Thank you very much.